Hello everyone, welcome back. Let's talk about another easy problem on Leetcode today. Number complement, Leetcode 476. In this problem, we are given an integer num and we should return its complement. The complement of the integer is the integer we get when we flip all the zeros to ones and all the ones to zeros in the binary representation. For example, for given integer 5, the binary representation is 101. Then the complement of it is 010, which is integer 2. And that they have also given in the example as well. So then they are saying that in the binary representation, there are no leading 0 bits. Now in terms of solution, there are multiple solutions possible. One of the easiest way can be that we can actually do the subtractions. Let's look at the binary representations of the number carefully. Let's take number 22 for example. The binary representation of 22 is 10110. If you want to understand how we convert decimal number to binary number, please check out the video here. Now let's look at the complement of 22. So we will make 1 to 0s and 0 to 1. So it will be 0, 1, 0, 0, 1, right? And now if we add these two numbers, we will get a number containing all the ones. So for example, 0 plus 1 gives us 1, 1 plus 0 also gives us 1, and so on. So to get the complement of number, we can actually subtract the number from the number of same size having all the ones in it. And now the question is how we can actually get this kind of a number. And there comes the interesting piece, that if we look at this number carefully, it is nothing but 2 to the power of number of bits in the number minus 1. So for example, if we take this number, it will be 11111, right? There are 5 ones in it, but if we add plus 1 to it, we will get 100000, so that will be 32, or 2 to the power of 5. So to get all the ones of size 5, we have to do 2 to the power of 5 minus 1. So basically we have to get number of bits in the number and then get all the ones by 2 to the power of number of bits minus 1. And then from this number we can actually subtract the original number and then we will actually get the complement. And now the question is how can we get those number of bits? And one way can be that actually we can use inbuilt function in Java. For example, Integer.toBinaryString number.length. So that will give us 5, for example, for 22 because there were only 5 numbers in it. And then to get all ones, we can just do Math.pow 2 to the power of bit length minus 1. So that will give us all ones, or better approach is to use the left shift operator because it involves bit manipulation and it is way faster than Math.pow function, which actually use floating point numbers. And now let's see how the left shift operator works. Let's take number 22 again. So we know that we can represent 22 as 10110, right? So the bit length here is 5. And now we apply the left shift operator on number 1. So if we do the left shift once, we will get 10. If we do the left shift twice, we will get 100. Similarly, if we do left shift 5 times, we will get 100000. So that will have 5 zeros after it, and then we can subtract minus 1 and we will get 31 again, which will have all the ones set in it. And then we can actually subtract 31 from 22 and we will get 9 as an answer, for example. Another way to get all ones can be that we can use inbuilt function in Java called Integer.highestOneBit, which returns an integer value with highest 1 or the leftmost 1 bit set as per the given input number I. So for example, if we take number as 22, then the binary representation is 10110. And if we want to get the highest bit set, that will be 10000. So that will give us 16. So this is what Integer.highestOneBit returns on number. And now if we do the left shift operator on it by 1, then we will get 100000. So that will give us 32. And again, if we subtract 1 from it, we will get all 1. So it will be 31 and then it will have all the 1s set in it. And now if the interviewer says that we cannot use any inbuilt methods, so then we fall to even more basics. So for example, we can actually use logarithm of 2 to actually get the number of bits set in the number. In Java, we use natural logarithms. So we use log base e, where e is I think 2.7 or something. And to get log 2 of a number, we need log of number in different base, in this case e, divided by log of 2 base e. So this is how we convert logarithm of a number from one base to another. So this will give us logarithm of number base 2. So this is what this statement is doing. So we are doing math.log of number divided by math.log of 2 to get logarithm of number base 2. And then we are adding 1 and then taking floor of it. So that will give us number of bits set in the number. So let's look at it with examples. So we know that 22 is 2 to the power of 4 plus 6, that is 16 plus 6. So if we take logarithm of it to base 2, it will be approximately 4 point something, because if we take logarithm of a to the power of b base a, then we get b, and here we are doing logarithm of 2 to the power of 4 base 2, so it will give us 4 plus 6. So logarithm of 6 will give us some more value, so that's why it will be approximately 4 plus something, and to be precise it's around 4.46. And now we add 1 to it, so we will get approximately 5 point something. And now if we take floor of it, we will get 5, which is number of bits set in it. Let's take another example which is easier. Let's take 16 itself, right? It will be 2 to the power of 4. And now if we do the log 2 there, we will get 4 and we will add 1 to it. So it will give us 5 again. And we know that 2 to the power of 4 is 1000. So we can see that there is fifth bit set here. So their number of bits is equal to 5 in this case. And then we can get all the ones using left shift operator by the bit length or n bits. I think it should be n bits minus 1. So that will give us 31. Another approach can be that we can actually use a left shift operator and bitwise OR operator. Let's denote all ones by n, and initially it will be equal to 0. Then till n is less than number, we can take a left shift on n, and then we can take a bitwise OR with 1. So let's take number as 22 again. And now when we left shift n equal to 0 by 1, we get 0. And then we do OR with 1. So that will give us 1. So now our n becomes 1. And we know that bitwise OR has following properties, that if we do a or 1, we will get 1, whether the number is 1 or 0. And if we do a or 0, we will get a. So if a is equal to 1, then we will still get 1 here. So now n is equal to 1. So we do the left shift operator. In the next iteration, it will become 1, 0. And now we do the OR on it. So we'll get 1, 1, that is 3. Then we continue because it's less than number 22. So then we do left shift operator. So it will become 1, 1, 0. And then we do OR on it. So we will get 1, 1, 1, 7. So 7 is still less than 22. So now we do the left shift operator again, do the OR on it. So that will give us 1, 1, 1, 1, which is 15. And n is still less than number. So we will continue. So now we will get 1, 1, 1, 0 or 1. So that will give us 1, 1, 1, 1, 1. That is 31. And now 31 is more than 22. So we will stop. And then this way again we got all ones. So now the logic is simple. Whatever we got as n, we can do n minus num. And that will be our numbers complement. Now let's see this in action. So we can say all ones equal to 0. Then while all ones is less than number, we can just do all ones equal to all ones left shift 1, and then we do OR with 1. And finally we return all ones minus number. Let's run this code. Cool. Let's submit this code. Cool. Another way can be that, like we discussed, we can just say all ones is equal to Integer.toBinaryString number.length. So that will give us bit length, right? So if we do the left shift operator on 1 and subtract 1 from it, we will get all ones again. Let's run this code again. Oh, it should be length function because it's a string. Cool. Let's submit this code. Cool. So there are multiple ways to get all ones. And instead of subtraction, actually, we can also use XOR. And the reason is, if you look, we have to table of XOR like this. So 0 XOR 0 gives us 0. And 1 XOR 1 also gives us 0. So only way we actually get 1 is if either of them is 0 and 1 or 1 and 0. So if the bits are different, then only we get the 1. So if we look at the binary representation of the number and all ones again, and we do bitwise XOR between them, then we will again get the number complement. And let's see it with examples. So if we do 1 XOR 1, we will get 0. Similarly, if we do zeros or 1, we will get 1. 1 or 1 will give us 0. Again, 1 or 1 gives us 0. And 0 or 1 gives us 1. So XORing with all ones is switching off the bits when they are on in the original number to 0 and switching on in case it is 0 to 1. So that's why bitwise XOR also works. So instead of subtraction, we can also do XORing. So let's test it out. We will do all ones XOR number, right? So let's run this code again. Cool. Let's submit this code. Awesome. And now let's look at one more method. How about we use bitwise complement or not operator itself? So when we apply the bitwise not operator on a number, for example, 22 again, 10110, then we actually flip all the zeros to ones and ones to zeros in the binary representation. So 1 becomes 0, 0 becomes 1, 1 becomes 0, and 1 again becomes 0, and 0 becomes 1. So bit flipping did work for these 5 digits, and they match the answer as well because our expected answer is 01001, right? But where we have a problem is that it is not limited to these 5 digits only. And all the preceding zeros before 10110 have become 1. And in the example, it was mentioned that we don't have any leading 0 bits. But in the actual number representation, all the zeros have become 1. So we have to switch off all of these ones to 0 so that it actually matches our answer. So one way can be that we add this 1 at this 6 bit. So 1 plus 1 becomes 0, then it carries over 1 to this digit, then 1 plus 1 again becomes 0 and it carries over and so on. And then all of these preceding bits become 0. And what should we actually add on the right of 1? It should be all zeros because if we do 1 plus 0, we will get 1. 0 plus 0 gives us 0. So that means these 5 digits remain unchanged. And what is this number? It is 2 to the power of 5. And in general, it is 2 to the power of bit length, which we already saw in the previous examples as well. So the idea is just get the complement of the number and add the 2 to the power of bit length to this number and we will get actually our answer. So now let's see this in action. So instead of doing all ones, we can get power of 2 and we can get it by left shifting 1 by bit length of the number. And then we just want the complement of a number plus this power of 2. And I'm writing in 2 different lines. We can also make it a one-liner. Even the previous solution can be a one-liner. But the important thing is you understand. So now let's run this code again. Cool. Let's submit this code. Awesome. And in terms of time complexity, it will be O of log n. And the reason for this is we are actually trying to get the bit length. So if you think of a number in binary terms, it will be 2 to the power of x plus something, right? For example, 22 was 2 to the power of 4 plus 6, right? And this additional number will be smaller than 2 to the power of x. For example, here we can see that 6 is smaller than 16 and 6 can be broken down into 4 and 2. So for simplicity's sake, let's ignore this number. And we know that in worst case, x can be equal to 32 because we are generally dealing with 32-bit integers. Now n is equal to 2 to the power of x. So if we take log base 2 on both sides, then we will get x is equal to log n base 2. So that was our bit length. And then we do the left shift operator that generally takes O of 1 time. So main task for us is to get the bit length and that is taking most of the time. So it is O of log n. And in terms of space complexity, it is O of 1 because we are using constant space. So that's it. I try to cover as many basics of bitwise manipulation as possible. Please like and subscribe if it was useful to you. Have a nice time. Thank you.